Welcome back. We're still discussing scatter diagrams and correlation. And in this video, we're going to talk about the difference between correlation and causation. So here's an example. According to data obtained from the Statistical Abstract of the United States, in the years since 1990, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers is 0.940. So let me say that again. The correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers is 0.940. So the question we're going to ask is, does this mean that births to unmarried mothers somehow causes women to obtain a bachelor's degree? And so we'd say, of course not. It turns out that in the years since 1990, both the percent of women with bachelor's degrees and the percentage of births to unmarried mothers has been increasing. And so it turns out that the correlation coefficient calculated for these two variables is quite high. However, it doesn't mean that one causes the other. They're simply both moving in the same direction over time. And in fact, this is quite likely to happen with what are called time series data. Data whose variables track some value over time. Over time, if two variables both happen to be moving in the same direction, or in opposite directions, we might compute a large value for the correlation coefficient. But that doesn't necessarily mean that one variable causes the other. The key point to make about this data is that it's observational. That means the data was simply out there and we collected it and did some analysis on it. And so it's important to remember that, in general, we can't claim a causal relation exists when we have observational data. We can only make the stronger claim of causality when we have data obtained through a designed experiment. Another way that two variables can be correlated, even though there's not a causal relationship, is through a lurking variable. Now, a lurking variable is some variable that's related to both the explanatory and the response variable, but was not considered in the study. For example, in certain areas of certain countries, monthly ice cream sales are highly correlated to drowning deaths. Now think about that for a second. Monthly ice cream sales and drowning deaths turn out to be highly correlated in certain areas. So as ice cream sales go up, drowning deaths tend to go up. When ice cream sales are down, drowning deaths tend to go down. Does this mean that local governments should shut down all ice cream shops? No. The lurking variable here is temperature. As temperature rises, ice cream sales and the number of drowning deaths unfortunately tend to rise as well. So we'd say that these two variables are correlated. They may be highly correlated, but clearly one is not causing the other. And here's another example from your text. This slide deals with a study where researchers were interested in whether consumption of colas was related to bone mineral density in women. And if we look at the scatter plot, we see what appears to be a linear trend in the data. More cola consumption tends to be associated with lower bone mineral density. And the correlation coefficient for these data turns out to be negative 0.806, indicating a strong negative linear relation between the two variables. However, this study was what's called a prospective cohort study, which is a kind of observational study where a group of people, that's the cohort, is followed and observed over time. So since it's observational, and the researchers are not deliberately manipulating any of the factors in the study, we can't conclude that increased cola consumption causes lower bone mineral density in women. In fact, there might be some other variables, we might call them lurking variables, that may or may not have been collected in the study that might be related to both cola consumption and bone mineral density. So what lurking variables might help to explain these results? Well, things like age, body mass index, whether or not someone smokes, calcium intake, etc. These other factors may be related to both cola consumption and bone mineral density. And so the end result is that, since this is an observational study, the researchers couldn't simply conclude that cola consumption causes lower bone mineral density, even though there was a strong correlation coefficient calculated for the two variables. What they were able to say was that increased cola consumption was associated with lower bone mineral density, but they weren't able to say that one variable caused the other. And so that brings us to the end of section 4.1. We want you to read pages 192 to 201 of the text, and note that we're omitting Objective 4 on page 200. And then we recommend that you try the problems in the book given here. And note that the odd-numbered problems are worked out in the Student Solution Manual on Course Compass, and you can find that manual by clicking on the Tools for Success button.